All right, today we're tackling a big one, Einstein's special relativity. This isn't just some dusty old theory. Nope, it's an idea that completely flips our understanding of reality on its head. So let's dive in and really unfold the universe and see it in a totally new light.
Okay, let me just start with a simple question, but one that might mess with your head a bit. What if space and time, the very things you take for granted, aren't what they seem? What if the distance between us right now and the seconds ticking by on your clock? What if they're not fixed? What if they're flexible? Even relative?
So, look, our everyday experience is pretty straightforward, right? Space is just the distance between things, and time? Well, that's the clock on the wall. They feel totally separate. But here's where Einstein comes in and just blows that all up. He said, nope, they're not separate. They're actually woven together into this single thing, a four-dimensional fabric called space-time. And honestly, getting your head around that one idea, that's the key. It unlocks everything else we're about to talk about.
Okay, so let's jump into this new reality. And just to be clear, special relativity doesn't just bend the old rules of physics, it throws the old rulebook out the window and writes a brand new one for the entire universe.
The most basic piece of this new reality, the fundamental building block, is something called an event. Now, in physics, this word is super specific. It's not just, something that happened. It's a single, precise point in space-time. Think of it like a coordinate. One specific location at one specific moment in time. A totally unique here and now.
Okay, so if reality is just a collection of all these events, then how in the world do we map them out? How do we see how they're all connected? Well, you can't use a regular map. You need a new kind, and that's where we get to the map of space-time, which we can actually see using something called a Minkowski diagram.
Building this map is actually pretty straightforward. So we start with an event. That's just one point on our map. Now, as any object moves through space and gets older, it traces a path across this map. We call that its world line. Simple enough? But here's the twist, and it's a big one. You don't measure the distance between two events on this map with a normal ruler. No, you use a totally new concept called the interval.
And this idea? This is absolutely the most important tool we have. Think about it. Everything else, your measurement of space, my measurement of time, it's all relative. It changes depending on how you're moving. But there's one thing that is absolute for every single person, every observer. That's the whole game right there. The invariant interval is the one true ruler that everyone in the universe can agree on. So what is this thing, this magical ruler? The invariant interval basically takes the distance in space and the gap in time between two events and mashes them together into a single absolute number. And the key word really is invariant. It means it doesn't change. It's unchangeable. I mean, no matter how fast you're flying through the cosmos, that value stays exactly the same. It is the solid ground, the bedrock that all of relativity is built on.
All right, so we've got our map, we've got our one true ruler, the interval. Now we can start to figure out some really deep stuff. And this next part is one of the most profound consequences of all this, the rules of causality. It turns out that the very shape of spacetime itself, it decides what can cause what. It's wild. You see that invariant interval we talked about? It's not just a random number. It actually tells you the relationship between two events. So if the interval is what we call time-like, it means they are causally connected. One can cause the other because a signal has enough time to get from A to B. If it's light-like, well, they're on the edge, only connected if a signal moves at the speed of light. And this is the big one, if the interval is space-like, they are completely, utterly, causally disconnected. It's physically impossible for one to affect the other. Nothing can travel fast enough to bridge that gap. So here's the main point, the thing to really get. The speed of light isn't just some random speed limit the universe decided on. It's baked into the very geometry of space-time. This structure is what stops things from getting weird. It prevents paradoxes. It's the universe's own way of making sure that cause always, always comes before effect. Okay, so we've got our map. We've got the rules of cause and effect. But what happens when things start moving on this map? Especially, really, really fast? Well, that's where we get into relativistic dynamics. And believe me, this is where things start to get truly mind-bending. In school, we learn that momentum is just mass times velocity. Easy.
But in relativity, not so simple. As something gets faster and faster, its relativistic momentum grows way more than you'd think. And as you get closer and closer to the speed of light, its momentum doesn't just get big, it goes vertical. It heads toward infinity. And since you'd need an infinite amount of energy to get infinite momentum, well, you can't. It's another deeper reason why there's a cosmic speed limit. It's like the universe itself puts on the brakes. And all of this, all of these weird rules about space-time and motion, it's all been leading up to this. Our final stop, the big one, the most famous revelation of them all. We are about to pull back the curtain on the ultimate secret that special relativity has to tell us about matter and energy. But before we get to the big equation, we need one last piece of the puzzle, something called rest energy. This was one of Einstein's most profound ideas. He realized that an object has energy just because it exists, just because it has mass. It's not about moving, it's the energy of being. So that cup on your desk, your chair, even you, just sitting perfectly still, you are a massive reservoir of untapped energy. And that leads us to this. This is the knockout punch. Mass isn't just stuff. It's not just the material that makes up the world. Mass is energy, a ridiculously concentrated, deep, and powerful form of energy. They're not two different things. They are literally two sides of the same coin. And you know the formula that describes this relationship. It's the most famous equation in history. E equals mc squared. It's so simple, but so powerful. The energy locked inside an object is equal to its mass times the speed of light squared. Now, the speed of light is already a ridiculously huge number. When you square it, it becomes astronomical. So what this little equation is telling us is that even a teeny tiny bit of mass is equivalent to a truly mind-boggling amount of energy. And look, this is not just some abstract idea on a blackboard. We see its power all around us. Every single second, the sun is converting its own mass into the light and heat that keeps us alive. That's E equals mc squared in action. Nuclear power plants, they work by unlocking that same energy from atoms. Even the simple, spontaneous decay of some elements, that's just a tiny bit of their mass turning into pure energy. This equation is literally powering our universe. So where does that leave us? Well, we've seen how special relativity just shattered our old ideas. It showed us that space and time are one thing and that mass and energy are another. It just makes you stop and think, right? If our most basic assumptions about reality were wrong, what else are we missing? What other incredible secrets about the universe are just waiting out there for us to find?